So today we're going to be doing our final round of hypothesis testing for this unit. We're going to test the difference between two variances. But now here's the thing. We did hypothesis testing for a single variance last unit, and we did our chi-square distribution. When we're testing the difference between two variances, we actually use a new distribution for us. It's called the F distribution. So just a little bit about that before we dig in, and here's the formula and all that good stuff. The F distribution is when we have variances from two independent samples are compared, and they are compared. You have your S sub 1 and your S sub 2 both squared because they are variances. So we have to be careful when we're making those comparisons. Remember, sometimes we're given, here's the sample variance, and we get to put it right in. Other times we're given, here's sample standard deviation, and when we substitute them, we have to square. So just be careful with those, and we'll talk about that as we go a little more today. Your samples are selected from two normally distributed populations in which the variances are equal. Some F distribution characteristics. The values of F cannot be negative. So it's similar to the chi-square distribution. Chi-square values cannot be negative either. The distribution is positively skewed. The mean F value, approximately equal to 1. The F distribution, it's a family of curves. We've seen this before. Our T distribution's family of curves. Chi-square is a family of curves. But typically we just have a single degrees of freedom that we look at. When we're using the F distribution, you're going to have a degrees of freedom based on the value of your variance in the numerator, and then based on your sample for your denominator. So there's going to be two different degrees of freedom that we have to use, one for the numerator, one for the denominator. So just a little glimpse of what the curves could look like. We'll kind of just draw that generic curve like we do with T and like we've been doing with chi-square as well. So we'll just kind of draw that generic curve when we try to look at our rejection versus non-rejection regions. The formula, it's probably one of the simplest formulas we do, but like I said earlier, be very careful. Those are sample variances. Those are sample variances. So if the data that we're given, or if we put data in our calculator gives us standard deviation. If we're given standard deviation, when we substitute in, we have to square our values. If we are given sample variance, we just substitute in, we don't square a thing. The squared, that exponent of 2, is part of the symbol for sample variance. So just be careful of that. We saw that last unit. The larger the two variances, and this is very important for us, the larger the two variances is placed in the numerator regardless of subscripts. The F test, we already talked about this, has two terms for the number of the degrees of freedom. The numerator, we take our sample size minus 1. Denominator, sample size minus 1. So finding the degrees of freedom hasn't changed, but we do have two separate ones. Here's the catch though. Your n sub 1 is the sample size from which the larger variance was obtained. So whatever variance value, whatever sample variance goes in the numerator for your F test, you have to make sure that the sample size matches up for your numerator. So you have to make sure you keep those things the same. For a two-tailed test, the alpha value is divided by 2, and the critical value is placed on the right side of the F curve. The reason why, I know it's a two-tailed test, but the reason why we only place it on the right side is because if we always put the larger variance in the numerator, our F value is always going to be larger than 1. So we're not going to have to be concerned with what's happening on that far left side. So that F value is always going to be larger than 1, so we're just going to have to concern ourselves with that right tail. Remember, our mean for our F distribution is typically right around 1. So it's going to be right about the middle of our curve. So if our F value is always larger than 1, we don't really have to concern ourselves with that left tail. We just need the right tail. So that's all we're going to get a critical value for. We'll place it on the right side. If the standard deviations, I already talked about this, if standard deviations are given, you have to square them. If your degrees of freedom, and this has held true for our t-distribution and for our chi-square distributions, if your exact degrees of freedom are not found in the table, we go smaller. So if we need degrees of freedom, let's say 23, and 23 is not in the table, but 20 is, we go with 20. We go below it. Our assumptions, again, we're not getting to be the researcher. We don't get to design the study and collect the data and all that good stuff. So when we're given the data, we need to assume that the samples were randomly selected, the populations are normally distributed, and the samples are independent of one another. Again, those are assumptions we get to make. We don't have to prove those. All right, so let's take a peek at our first example. Let's dig in. Just go ahead, take a minute, read through it. Now what I like to do, I know what we need to do is identify which is going to be our variance from our first, so which is going to get our subscript of 1, and which is going to get our subscript of 2. We have to identify those things first, just like with our mu's and with our p's for proportion. We have to identify which is which because we do have 2 separate samples. Now before I identify this though, what I like to do, if my larger variance has to go in the numerator, I like to find those variances first. I like to label whichever one has the larger variance, I like to put that with the subscript 1. Otherwise, what I find happens is if I label them whatever, if I put chocolate first, non-chocolate second, if non-chocolate has the larger variance, it messes me up a little bit when I go to do my degrees of freedom. We want to put our larger variance in the numerator when we find our F-test value. So I like to label whichever one has the larger variance. I like to label that with my subscript of 1. So do a little plugging and chugging in the calculator. I wanted to make sure we refreshed on how to get our variance from our calculator. I want to make sure we refresh on that. So go ahead and enter your data for chocolate into list 1, non-chocolate into list 2. And if you're interested in using, there is a calculator test for this. If you're interested in doing that, we will do that together. We're going to need the data entered in anyway. So go ahead and enter those things in. So once you have your information listed into L1 and L2, we put chocolate into L1, non-chocolate into L2. We go to Stat, Calc, and we want our 1 variable stats. I'm going to do list 1 first. Make sure your frequency list is cleared out. We don't need a frequency list. We're going to calculate. Keep in mind, the big reason why I wanted to go through this with you, your calculator only gives you sample standard deviation. We need to use the SX. We need to use the SX. Rounding rule, we should round to just 1 more decimal place value than the data we're given. So we should round to 6.5. We should round to the nearest tenths, 6.5. Now, if you wanted to, I know we need to enter the variances in. If you wanted to, remember, we can go vars number 5, statistics. And there we see number 3 is the SX. So vars, statistics, and then we see the SX there. If we put that, if we hit enter on that, square it, it gives us our sample variance. So the calculator will do that for you. It will store the exact value for that sample standard deviation for you, and then you can square it. Now, if you just want to go with the 6.5 and then square that, put that in the formula, that's okay. This is just another option for you. Again, I went to vars, statistics, and then you'll see the SX there. On my calculator, it's option number 3. Put that on your home screen and square it. To get, though, here's where you have to be careful. You can get the same information for our second list, so stat and calc again, but you just have to change your list to list number 2 for the non-chocolate piece, or wherever list it happens to be. And I know some of you, your list 1 and 2s have disappeared. Again, we need the SX, the sample standard deviation. And in this case, we'd round to the nearest tenth, be 11.2. Again, this is just standard deviation. We need variance. You can take the 11.2 and then put it in your F formula and square it. You can. Or we can go VARS, statistics, SX, and then square it. It'll just give you a more exact value. Either way is okay. I'm fine with whichever way you want to do. Either way is okay. So if we go back to our example, we had that our non-chocolate, our standard deviation for non-chocolate was roughly 11.2. For chocolate, our standard deviation was roughly 6.5. So again, what I like to do is I like to label whichever one had the larger standard deviation, or in this case, it'll lead to the larger variance. I like to label that as my number 1. And I'm kind of out of space there. Again, the only reason why I like to do that is so it helps me make sure that I put the right value in my numerator for my F-test value, and that I'm also using the correct degrees of freedom, the correct sample size, for when I find my critical values using Table H. So let's go ahead and state our hypotheses. And as usual, our null hypothesis is going to state that there is no difference, or in other words, the two are equal. You can actually show the difference if you'd like. How do I know it's supposed to be a difference of just 0? Because I'm not given any other hypothesized difference. I don't want to know for the grams of carbohydrates that the variance has a difference of 7 grams. I don't have a specific difference. So if no specific difference is hypothesized, we go with 0. The alternative hypothesis, all we want to know, is there enough evidence to conclude that there is a difference? There's not a specific difference given of that it's greater than or less than. So we just go the not equal, just showing that there would be a difference. Again, you can state those either way, with the differences or without. That's fine. Step number 2, we're going traditional, so we do need critical values. There is not an inverse F on your calculator. So to find critical values, you all are going to have to use Table H. Even the program in the calculator, it doesn't give you critical values. So we do need Table H. Table H, shoot, I don't have the page values. Anybody on Table H? 792. Table H starts on. Now, as you look at Table H, and you're definitely going to want to open, even if somebody next to you opens, that's fine. Again, you all will have to use Table H to find critical values. There's no inverse F on your calculator like for inverse norm and inverse T. There's many pages to Table F. How do you know which page you need? It's based on your alpha value. It's based on your alpha value. Now in this case, it's a two-tailed test. So we need to divide alpha by 2. Let's get a little more information down here. Our alpha is 0.01. Two-tailed test, so we're going to divide alpha by 2. We need degrees of freedom for the numerator. DFN is how I'll abbreviate that. Let's go lowercase, that's what we've used. Degrees of freedom numerator, and we need degrees of freedom denominator. The degrees of freedom for your numerator comes from the sample size of your larger variance, or standard deviation. You can look at it either way you want. The larger standard deviation leads to the larger variance, either way. So if we take a look, we had the non-chocolate was our larger standard deviation, so eventually larger variance. So degrees of freedom, we had a sample size for non-chocolate of 11. So the degrees of freedom for the numerator will be 10. Again, this is coming from the non-chocolate because it had the larger variance. I know we only have standard deviation written, but larger standard deviation means larger variance. And then degrees of freedom for the denominator will come from the sample with the smaller variance, or in this case, standard deviation. And we had 13. So degrees of freedom denominator is going to come from the chocolate, again because it has the smaller variance. So the degrees of freedom for the numerator, we take the sample size with the larger variance, subtract 1. Degrees of freedom denominator, sample with the smaller variance, subtract 1. So now on to table H we go, now that we have the little background info we need. And I need the page 4.005. So that should be the very first page. Mine's kind of blurry up here. 0.005 should be that very first page. Now we need degrees of freedom. The numerator is up in that top row. Our degrees of freedom for the numerator we said was 10. And then degrees of freedom denominator we had as 12. Again, you have to pay attention to making sure you have the right page of table H. It's all about what your alpha value is. In this case, two-tailed test, alpha has to get divided by 2. So we follow over, follow down. Our critical value is 5.09, excuse me. Critical value 5.09. All right, for step 3, our test value. One of the easiest formulas we have. Larger sample variance goes in the numerator. Smaller sample variance goes in the denominator. In this case, we only know sample standard deviation. So we put the larger one in the numerator, and we do have to square it, because we're only given sample standard deviation. We need variance. We get roughly 2.97. How do I know what to round to on the test values? I always go to the same amount of places as my critical value. So whatever my critical value is rounded to, that's what I go to for my test value, because we have to compare those two things. So if we draw a little picture, again, it's a family of curves, so what this exact curve looks like, we don't know. So it's positively skewed, so that means it's kind of like the chi-square. Bigger chunk of our information's off to the left, a tail goes off to the right. Critical values at 5.9, so somewhere out here. 5.09, I don't know why I keep saying 5.9. 5.09. 2.97 will be somewhere this way, off to the left. Again, keep in mind, this is similar to chi-square, where we have a 0 on the far left. These values will never go negative for us. Variances cannot be negative, so this distribution will never go negative. So our test value ends up in our non-shaded, non-critical region. So do not reject. Our null hypothesis. Ooh, we never identified our claim. Shoot, that's a big important step I skipped. We want to conclude that there is a difference. So the claim will be our alternative. And a lot of you probably actually wrote that on your paper, and I didn't write it up here. So if I don't reject the null, I can't support the alternative, which is my claim. So there is not enough evidence to support the claim that there is a difference between For this second example, just take a minute and read through it and think very carefully before you label which is going to be your 1 and which is going to be your 2. Alright, so if you take a read through, you want to put, and again, this is just to make things simpler, we want to try to keep our larger variance in our numerator. So what I like to do to make sure that I don't get goofed up with the different symbols, whatever sample has the larger variance, or in this case standard deviation, I put that as my first one. So then all my labels match up. It helps me avoid confusion when finding my test value and finding my critical values with my degrees of freedom for numerator and denominator. Alright, so I'm going to label as our first one. Which one has the larger one? Looks like dogs. And our smaller one is cats. And again, I'm just basing that purely off of which one has the larger standard deviation, which would in turn lead to the larger variance. Alright, so we have those labeled. So when we state our hypotheses, you have to be careful. Slow yourself down when you write that alternative hypothesis. Now we are hypothesizing about the standard deviation, so our symbol should just be the sigma without the squared. So just be careful when you write your hypotheses. Alright, then we want to show standard deviation of the ages of cats is smaller than that of dogs. So we do have a greater than symbol. We do have a right-tailed test for our alternative hypothesis. Because remember, we made dogs our sigma sub 1. So we want to show that the dogs are larger or showing the cats are smaller, whichever. So I have to be very careful with your labels. Be very careful with your labels. Alright, step 2, we're talking critical values. It's just a one-tailed test. We don't have to divide alpha by 2. Alpha is going to stay at 0.05. Degrees of freedom for the numerator. We need to look at our dogs. So we're going to have 16 minus 1 is going to be 15. Degrees of freedom denominator is from our cats. So 29 minus 1. Degrees of freedom denominator be 28. Let's go to our table. We need to find the page for 0.05. Degrees of freedom for our numerator, 15. And our table does actually have a 15. Degrees of freedom denominator, 28. And we're lucky we do have a 28. We go over, we go down. Oh, mine's a little smudged there. Is that 2.04? Yeah? Okay, thank you. So 2.04. test value, one of the easiest test values you're going to find. Standard deviation, so we have to square it. Standard deviation, so we have to square it. Roughly 1.68. You can draw a little sketch if you need. 2.04, somewhere over here. It is right-tailed. 1.68, it's pretty close, but it's not in that rejection region. So again, there's not enough evidence to support the claim that the standard deviation of the ages of cats is smaller than that of dogs, or something along those lines. Now, as promised, there is, and some of you have already discovered it, I said, hey, go ahead, it's on page, what did we say? It's on page 537, the calculator stuff. We will get to that, but I do just want to show you, if you do have to do p-value for this, and if you're not using the calculator program, I do want to show you what it takes to use the table. I'm just going to do one of these. What it takes to use the table to find a p-value for an f-test. In order to find a p-value for an f-test, you have to actually look at every alpha and then the f-test value that goes with it. So you have to look at each page of table F, use the proper degrees of freedom numerator denominator, and find the value in the table that matches up with it. So for example, if we're going to make ourselves a little table here, the first page of H is 0.005. So what I'm going to do is if I go to table H, again, if you are not really a calculator person, this is definitely going to be for you. I'm going to go to table H. I'm going to go to the first page of it. Let's see if he'll let me erase these things. And what I have to do, and then I have to do this for each page of the table, is I have to go degrees of freedom numerator, in this case is 6, degrees of freedom denominator is 10. I have to find the given value in the table. So for each page, so for each alpha value, each page of table H, you have to go to the correct degrees of freedom numerator and denominator and find the value from the table. That value you are then going to list in your little table that you're making. So next we go to where alpha is 0.01. So next we go, alpha is 0.01. Degrees of freedom numerator was at 6. Denominator was at 10. And we end up with 5.39. So you continue that process. The next page would be 0.025. You'd continue that process till you have all of them jotted down. So you make your own little table. And again, you use your degrees of freedom numerator and denominator. You have to go to each different alpha value, so each different page of table H. Go to the correct degrees of freedom numerator and denominator and find the value in the table. So you make yourself your own little table here. And that's just because table H is so spread out. This is something that's really easy for us to do when we had the table for the t-distribution or even chi-square. So it was just one page of a table. This has 5 different pages to it, so you have to go through and find the value on each page. Then what you do, same as what we've been doing with p-values, you go across your row for f, and you find where your f value either is or where it falls between. This one happens to hit right on that our p-value would be two-tailed test, so we have to double it. Our p-value would be 0.05. If it's not a two-tailed test, you don't double it. If your test value, let's say it happened to fall between two of them, just like we saw with the t-distribution and with chi-square, you would make yourself a little interval. So let's say we had the same table. Let's say our test value was f equals 3.75. 3.75 would fall between those two. So then we would do a little interval like we saw with chi-square and with the t-distribution. Again, you only have to do this if you choose to use the table for p-value. So now I know some of you are thinking, that seems like a lot of work. So maybe for this one, I'm definitely going to look at the calculator option. So the calculator option, we go to Stat, we go to Tests, and then for this one, you have to scroll down a little ways. To a 2-sample f-test. It's option E on my calculator. It's a 2-sample f-test. We already entered our data in from that first example, but now here's where you really have to watch yourself though. We put chocolate into list 1 and we put non-chocolate into list 2. But then when we labeled our sigma sub 1 and sigma sub 2, we switched them, because we found out that non-chocolate had the larger variance. So you have to make sure that you have the sample with the larger variance as your list 1. You have to make sure you switch that. And the only downfall is when you have to enter the data in your calculator, when you don't know the sample standard deviation or variance already, you don't know which one it's going to come out to be. So you have to make sure you find each of those and figure out which list you want to put that in. For the first one, we had a two-tailed test. Calculate it. And then notice your calculator will give you the p-value. So this one might be worth checking out, even just for the sake of finding the p-value, because p-value does take a little bit more work if you're using the table for this one compared to a t-test or compared to what we did chi-square last unit. So this one might be worth checking out just for the p-value alone, I would say. All right. So again, calculator stuff, that's on page 537. So if you want to check that out, you sure can.